Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this course, and today we are going to turn our attention to the next chapter of fracture mechanics. For this particular subject, I am going to follow this e-book, what you are seeing on the screen, written by Professor K. Ramesh of Applied Mechanics Department in our institute, and Professor Ramesh himself is offering a full-fledged course on fracture mechanics in the NPTEL platform, and it has been now running for many years. And I urge all the students to do that course as well if you have a complete knowledge of fracture mechanics, which is almost 55 hours of lectures, almost a 4-credit course. And I decided to follow this book because this book is designed very specially with a lot of animations, what you are seeing on the screen here, by Professor Ramesh, who has done a commendable job, and is also my teacher, and this is published by IIT Madras itself. So I thought, I will use this book for taking the fracture mechanics course in our department as well, because all these animations not only are beautiful, and they also motivate the students to look at them, and it creates a lot of awareness about the concepts, and it's very interesting. Okay, so we will start this chapter by just looking at historical development. Study of elliptical holes in a tension strip by Inglis 1913 has brought into focus the severity of a crack in a structure. We are going to see the details of this, what Inglis has proposed, and but this is the one first event which is triggered the idea of severity of the crack. Okay, then followed by Griffith in 1920, who considered the propagation of cracks in glass and developed right ideas for a crack growth. So this is again very important. Okay, after several years, Griffith has developed some ideas for the crack growth. So this is just a second event. And he also formulated that an existing crack will grow provided the total energy of the system is lowered by its growth. So this is something like what we do in thermodynamics, like lowering the energy of the system, but he coined right parameters to capture this idea. We will see how it is. Very interesting theory. But his work was not noticed at that time due to the exigencies of the World War and the following depression worldwide. Griffith was not able to coin a convenient parameter for predicting the failure load of a component through the growth of a crack. So this is some of the initial struggle. Okay. But what happens is he did provide a good theory. Then before, and he coined that parameters for brittle materials like glass. Okay. So what you are now seeing is a concept called healing of crack. What is healing of crack? You see this material shown in this animation, which is a non-metallic material, which is being pushed by a ballpoint pen. So what you see, there is a edge crack from the outer surface, and then the moment the ballpoint pen hits on the plate, what do you see? There is a crack growth or crack extension towards the inside of the plate. Okay, the moment the load is removed, what you see? Again, the crack is closing. This is very important. So Griffith's ideas were rightly captured in this kind of material. He proposed a very nice balance theory for crack growth and crack closure as well. So we will see how these ideas are developed. And this animation clearly shows, it's a very simple, a day-to-day kind of an activity in your in your workplace. And then, we don't bother uh, how this crack is growing and all that. But then if you pay attention, it is quite interesting to appreciate what the science behind it. Okay, so we will see one by one. The next item is crack growth speed. Okay, it's a shadow photograph of a crack branching process in a plate of glass. So I'll play this animation. So what you see, this is a crack is growing and then stopped here and then it started branching. But if you look at this animation carefully, the crack comes with a speed and then it accelerates and then it stops and then grows. Note that increase in the crack speed beyond the crack speed is bad. Beyond the crack speed, it branches. So that means at what stage a crack tend to branch? This is again a very important question, and Griffith has provided a very nice solution for this. Okay, we will see later. The elaborate photoelastic analysis has predicted a crack cannot grow beyond a Rayleigh wave speed. Okay, so beyond that, what happens, and then why it branches, and what is the science behind it? These are also some curiosity. It also a curiosity level questions, so we will be able to answer it during the course of the time. So now, if you look at the branch, fracture mechanics is a broad area covering several disciplines. Like I mentioned in the beginning, this branch is being applied in different disciplines like mechanical engineering, applied mechanics, engineering design, aerospace, civil, materials, and so on. But if you look at in a nutshell, which is connected to material science, NDT, and the stress analysis and design. How they are connected? So if you look at the material science aspect, then this branch takes care of or the studies of fracture process, and fracture toughness. So these are all elaborately focused in this subject domain. But what does this NDT do? That is non-destructive testing. NDT takes care of crack detection. Okay, it's how to find out the flaw size. How to identify the flaw and then the flaw size, and then crack growth monitoring. You can also monitor as a function of time by NDT schedule. And then most important thing is again the stress field evaluation. Okay, which is done by the other branches, engineering branches. And then damage tolerant design. What is damage tolerant design? You have inherent flaw. All the structures will have an inherent flaw. You measure them and then predict the life. Okay, how long what is the critical size of the flaw? Okay, how long the remaining life of the component, or how long that will take to fracture, something like that. So that is called damage tolerant design. In that you have a safe life design or fail safe design. So there are two concepts. We will see all of them. In a fail safe concept has different aspects. Again, multiple load path, design for crack arrest, and then leak before break. So we are talking about the design for a crack arrest. We are talking about there is a design we can do where the crack, we have just seen the crack closure. We can also see that some aspects which can give the crack arrest. And the next one is very important, leak before break. That means before the fracture, your system should give a sufficient warning. See, if you take a simple tensile test, so before the fracture happens, you have enormous amount of yielding. It goes through yield point and UTS and then fracture, something like that. You have, it is very important for the nuclear or power plant applications. Without that, these are all going to be very difficult. So these kind of designs are useful, and which is provided by this subject. That's what we are going to see. So fracture mechanics attempts to account for existence of inherent flaws in structures and thus is closer to reality in modeling engineering problems. That's what I just said. It uses stress analysis to determine the stress intensity factors, material science determined to fracture toughness, and NDT to determine the initial process. You see, the stress analysis comes out with a parameter called stress intensity factor. We will see it. It's called K. Okay. So all the stress intensity factors is evaluated by the stress analysis, and the material science, as I mentioned, takes care of the fracture toughness measurements, NDT, initial process. Design for a given safe life is possible if the above mentioned three inputs are available. So all these three are forming a primary basis for the design. Okay, LEFM and EPFM. What is LEFM? Linear elastic fracture mechanics and elasto-plastic fracture mechanics. We are going to see them also. Okay, what are they? Structures made of ductile high strength alloys failing in a brittle fashion prompted the birth of fracture mechanics. Okay, this is the bottom line. Okay, why fracture mechanics becomes so important? Because people believe that ductile high strength alloys, which you can't, people never imagine that it will fail in a ductile fashion. Okay, so then people started looking at them seriously. So linear elastic fracture mechanics, which deals with extension of Griffith's ideas for ductile solids to ductile, sorry, ideas for brittle solids to ductile high strength material, was done by Irwin in 1948. Though Griffith gave ideas for only brittle solids, Irwin extended those to high strength materials. You have to understand, it is just only for high strength materials. The main focus of Irwin's theory is on the crack tip rather than the crack, by moving the analysis to the crack tip. We will see why we are talking about a crack tip here, because initially the crack was crack length was measured, and then the analysis started from the center of the crack. The moment the attention shifted from the center of the crack to the crack tip, there were quite, the scenario was quite different. That is why it is mentioned like a crack tip. Irwin devised workable parameters like stress intensity factor and energy release rate. Very important. So we are now talking about parameters called stress intensity factor. I said that comes out of the stress analysis, elaborate stress analysis, and also the new term, energy release rate. This is another parameter which governs the crack growth. Okay, the energy for the crack to grow. That describes that description also we will follow now, which is all part of LEFM. LEFM accounts only for a small scale yielding near the crack tip. See, linear elastic fracture mechanics does not consider the plasticity. That is what it means, right? So it can only accommodate a small scale yielding which is close to the crack tip. It cannot handle major plastic or yielding phenomenon. Then you have to move on to elasto-plastic fracture mechanics. LEFM is quite useful for analyzing problems in the aerospace structure. So far, LEFM concepts only serving the full aerospace structures. Okay. And if you look at elasto-plastic fracture mechanics, what are the features? For example, role of plastic deformation near the crack tip is better accounted in EPFM. For situations where the material behavior is non-linear, such as in nuclear applications, elasto-plastic fracture mechanics is essential. Typical materials for which LEFM is applicable at room temperatures are high strength steel, precipitation hardened aluminum, polymers below glass transition temperature, ceramics, and ceramic composites. If you see in the previous chapters, we also looked at the polymer behavior, right? We looked at tensile deformation, we looked at creep deformation, and how the viscoplastic models and all that we have talked about for polymers. So here also you can see that LEFM LEFM can be applied to this kind of polymeric material below TG and ceramics materials and ceramics composites and so on. So if you typical material for which EPFM or a nonlinear fracture mechanics is applicable are low and medium strength steel, metals at high temperatures or high strain rates, polymers above glass transition temperature, ceramics at high temperature. So it is quite obvious. We have looked at all these parameters, like we looked at room temperature deformation, we looked at high temperature deformation of where all these materials. In fact, elaborately, we also looked at the creep behavior. So now you will have a nice background to appreciate whatever we are just mentioning here. So what is the range of LEFM, EPFM? It is to be noted that fracture mechanics based engineering design looks at brittle failure of structures. The plastic zone is very small and highly localized. And then how do you visualize this? How do you visualize this plastic zone? So if this is a nice schematic where the high strength material in a plane strained condition, and you see the crack which is there, and you can also see that high strength material in a plane stress condition. In these two scenarios, LEFM is applicable, where the plastic zone is very small and highly localized. You can see that. I can just show it in a zoomed manner. So you can see that very small plastic zone. Yeah, go back. So, and what is the next? More ductile material in a plane stress or plane strain condition. And then you can see that the ductile material with the spread of plasticity, the plastic zone size is very big. You can see that. And in such a situation, it is better to, or the EPFM is highly useful. Okay, but the extreme cases, for example, the ductile material which is fully plastic, that means the plastic zone is completely occupied the entire specimen, then it is explained only by plastic collapse. Okay, none of this theories will be useful at that kind of a situation. That's what it's. Now we look at modes of loading in fracture mechanics. Most of the analysis is done by three modes. The mode 1 is opening mode. The schematic is nicely shown here, where you can see that the crack surface once it opens. Loading is normal to the crack surface, and displacement of the crack surface are perpendicular to the plane of the crack. So one of the most common and dangerous loading for crack growth. So we are trying to introduce what is mode 1. Okay, basically nothing more than that. We will look at the details as we progress. Okay, we are only just introducing this. Mode 2 is also called sliding mode. Loading is on the crack plane, that is in plane shear. It is also called in plane shear. Displacement of the crack surface is in the plane of the crack and perpendicular to the leading edge of the crack. Okay. In many instances, the presence of mode 2 loading is to alter the crack growth direction. So we can also, interfere the crack growth, okay, by adjusting the loading. So this is one of the idea. So the mode 2 is also called sliding mode. Mode 1 is called opening mode. Okay. So what is the third one? Third one is tearing mode. Mode 3, or it is called tearing mode. This mode is caused by out of plane shear. Okay, so this is a shear stress direction, and obviously the shear is out of plane. So you can see that. And the displacement of the crack surfaces is in the plane of the crack and the parallel to the leading edge of the crack. Paper is usually separated by a tearing action. See, if you give a paper to somebody, or if you want to tear a paper, you intuitively, you just tear it in the tearing mode. We don't think fracture mechanics when we tear the, paper. But naturally, we do the tearing mode, right? So that is what it is shown here. So if you look at the summary of all these three, it is mode 1, mode 2, and mode 3. They are shown in this slide just to see the difference between the animations. You can see that. So like I mentioned, the stress analysis will arrive at different stress intensity factors for all these modes, and then the correspondingly in material science will evaluate a parameter called fracture toughness K1C, that is critical stress intensity factor of mode 1, or mode 1 critical stress intensity factor, mode 2 critical stress intensity factor, which is also called a fracture toughness in material science. But in a stress analysis, we will term it as stress intensity factor to start with. So this is a kind of introduction to modes of failure. So what the fracture mechanics should be able to answer? Fracture mechanics should be able to answer the following questions. What is the critical length of the crack? Okay, what is the critical length of the crack? Okay, so we were talking about NDT monitoring, right? So what is the critical length of the crack? For a given length, what is the residual strength? So you know the critical crack length, then how long this structure is going to last before it fracture? That is again a question. What is the time that would take for a crack to grow? So in a crack you have two phases, okay, a growth phase and then fracture. That we will see it. So what is the time that would take for a crack to grow? Okay, that is also very critical. How is NDT schedule decided? What causes the crack to branch? Just we talked about it, right? What are the energy dissipation mechanisms? Very interesting questions. All these questions will be addressed by this subject. Okay. So, new test for fracture mechanics, basically just to monitor the crack. You see that this animation clearly shows this is a compact tension specimen where the notch is made, and you see that a crack is grown by fatigue loading. Basically, delta P is the amplitude of the loading, and this there is a probe which monitors the crack growth. Okay. So the crack length is measured as a function of number of cycles to failure, and this is for a different amplitude, you see. And from this you cull out a data that is dA by dm versus log delta k. We will give you a straight line. So this is a crack growth plot. This equation is called Paris law. dA by dm is equal to c into delta k to the power m. We will look at the details of this Paris equation and materials implications in detail in the later part of this course. Okay. So we are now looking at the overview, and what you are seeing is here, when we talk about fracture mechanics, fatigue by default comes into the discussion. Okay, because you see, whatever the uh, discussion we had in the previous chapter, mostly we dealt with the deformation, and from this fracture mechanics onwards, we are talking about a fracture. Okay, so if you recall, in the beginning of the course, we just showed the whole subject, mechanical behavior of materials, into two domains. One is a deformation, another is a fracture. Okay, now we are talking about a fracture, and this fracture mechanics, by default, the crack is, the crack growth is discussed because the fatigue crack growth is primarily a mode of method to grow the crack in the material and then study this. So they are all interconnected. So you cannot really separate them. It's a fatigue, fracture, and fracture mechanics study. So that's one point I just want to drive home in this slide. So what you are seeing is a schematic representation of fatigue life, showing the relative proportion of life for a crack initiation and propagation. You see, this is a plot of alternating stress range delta sigma versus fatigue life. What you are seeing here is very interesting plot. You will understand this more in the later part of the course, but the point we want to emphasize here is the crack growth is essentially involves crack initiation period and crack propagation period. So very important. If you look at the as the stress range comes down, the crack initiation period is keep on increasing. So the majority of the life, what is important to note is the majority of the life of the component is spent on the crack initiation period rather than the crack propagation period. Okay, this is something very important. So that's why it is brought here. And this is delta sigma C is called fatigue limit. We will see it. What is the importance of this fatigue limit? Every material is characteristic of, every material will exhibit a characteristic fatigue limit. We will see them in the due course. And there is something called a residual strength diagram, which comes out of all these crack growth experiments. And you have the service load, and then you have a design strength, which is a reference, and then you look at the crack size, how it grows, okay, and then what is the maximum service load and what is the corresponding crack length. If you have this crack load plot, you will be able to get this. So AP is a permissible crack length. So you look at AP, that is a crack length which is against the sigma max. AC is a critical crack length which is given by, which is related to AP by AP is equal to AC divided by NC, where NC is a crack length safety factor. Okay. And we'll also see that how the crack growth curve will look like as a function of time, the crack size, and then there's a time plot which looks like this, and then you can also take this data as a function of time t1, t2, how the crack is growing, okay, and then time available for inspection, the total life. So this kind of idea will enable us to schedule the NDT tests and so on. This is kind of a real-time practice in engineering structures or structural monitoring or health monitoring of the equipments and so on. So what Professor Ramesh describes is fracture mechanics is a holistic methodology, something like in a medicine field, homeopathy does not treat the symptoms but addresses the root cause of a disease through symptoms. And likewise, fracture mechanics starts with premise that any structure can have internal flaws, and it attempts to account for them in design. Okay. So similar to homeopathy, in fracture mechanics, one finds a different recommendation for handling thin structures, which is considered as a plane stress, and the thick structures as a plane strain. So what Professor Ramesh's view is that in fracture mechanics, you have solutions for a case specific. Okay, for thin specimens, particular type of recommendation; for a thick specimen, particular type of recommendation is given as a solution for the crack problems. Further, the process-induced anisotropy is accounted for in the fracture testing and design. This is also another aspect to look at it. This slide is very important slide, and which describes the fracture parameters. Okay, summary. What are the fracture parameters? G, that is energy release rate or crack driving force, which is the energy based parameter proposed by Griffith. So the G is after the name of Griffith, and the next parameter is K, stress intensity factor, which has got a unit of MPa square root meter. We will spend some time on this unit, how to understand this later, which is stress based, and which is proposed by Keyes, a collaborator of Irwin. So it is known that the K is after the name Keyes, a collaborator of Irwin, just to honor him. And another parameter is J, which is measured in Newton per mm, called J integral, again an energy based parameter proposed by J.R. Rice. And the last one is CTOD or COD, crack tip opening displacement or crack opening displacement, which is measured in mm, which is a displacement based proposed by Wells. It's basically from UK. And what you see here is the first two parameters are applicable for LEFM, and the later ones are applicable for Elasto-Plastic fracture mechanics. So very important slide to remember. We are going to look at one by one in the course. Now I would like to just show some of the typical failures initiated by the crack. This is an helicopter blade reaching the bolt hole fracture. So what you see here is it's a very nice fractograph. So you can see that crack growth has taken place. It's a crack growth phase, and this is a fracture surface. So there is, as I just mentioned in the previous slides, that every crack has got a two phase. One is a growth phase, and that's a catastrophic fracture. So this is very important. And this crack is originated at a corrosion pit here, and this is a real-time, fracture surface. The other typical example is it's called typical failures initiated by the crack is shown here. This is what is this cross section? This is a cross section of a ray. So this is a crack, but what is interesting is the crack is not initiated from the surface. Usually fatigue cracks, or for that matter any other cracks, normally initiated from the surface, but this crack is just initiated below the surface. So what does it mean? How do we describe this? This crack is described as kidney because of the shape, kidney shaped crack, or detailed crack has initiated fracture of a rail section. This has been a topic of study for the past 20 years. Usually the older rail sections are found to fail by this. So how do we understand this? So rail failure means it is basically through the contact fatigue, right? It is not a surface. So any contact loading, the fracture does not, occurs on the surface. It is just below much below the surface. So this also will be explained by fracture mechanics nicely. Why a crack, occurs much below the surface when it is a contact loading. Okay, so stress analysis clearly says that the stress concentration is not at the surface but much below this. So we will also look at it later. So this is one example of very contact fatigue loading. So the other one is a failure of a bolt due to hydrogen embrittlement. Cracks have initiated due to stress corrosion cracking at two sites. So this is a bolt. So you are seeing a crack one which is grown here. The other crack is here, which is grown from this surface. So there are two cracks. They are all emanated because of the stress corrosion cracking. In fatigue failure, normally the first or the second thread fails. Here the failure has occurred a few threads below due to stress corrosion cracking. So it is not just a stress concentration alone, it is also because of the chemical attack combined, so-called stress corrosion cracking. This also we will see it when we discuss the crack growth mechanisms. This is one of the crack growth mechanisms popularly known. This is another example of inherent flaw in the aircraft engine crankshaft. So the flaw shape could be modeled as elliptical crack. So this is a crack which is shape appears as an ellipse. So just to give a visual impression, so this animation is done. So this is an example from the aircraft engine crankshaft. So these are the crack propagation from a circumferential groove of a shaft under torsion. So we are now looking at a different type of failures. This is under torsion. You can see that how the crack propagated. The crack growth pattern in a shaft subjected to low amplitude mode 3 cyclic stress intensity factor. The growth pattern in a shaft subjected to high amplitude mode 3 cyclic stress intensity factor. So all of them are characterized with the what type of uh, mode of failure, and then what type of stress intensity factor has been recommended for evaluating this kind of failure. Okay, so this is one example. Another example I just wanted to show. So this is a photoelastic visualization of crack tip stress fields, just to give what kind of a stress distribution in the crack tip. We were talking about the crack tip. So anyway, we are not going to discuss them in detail, but this is just to give you an idea how photoelasticity visualizes the crack tip stress fields. Okay. We will discuss about the stress fields, but we will not get into the photoelasticity one, but it gives you an overall very nice visual impression about this stress distribution around the crack tip. Okay. So I will stop here, and we will continue the lecture in the overview lecture in the next class. Thank you.